Hello, graph theory. Today we are going to discuss the planar circuits. The planar circuits are the circuits or planar graph or the graph which have no intersection of edges. So there is no intersection of edges. So we will use different kind of graphs. Uh, K1, one vertex, planar. K2, two vertices and one edge, planar. K3, three vertices and three edges, planar. K4, four vertices and six edges. One, two, three, four, five, and six. The five can be six is fine. Five can be represented like this one. So this one, this is five. This is a planar. K5, five vertices and 10 edges. So these vertices 1, 2, 3, 4, 5, and edges 1, 2, 3, 4, 5, and this is 6, this is 7, this is 8, and 9, 9 from this one to this one, and 10 from C to B. These can be represented like this one. So edges 1, 2, 3, 4, 5, 6, 7. 7 till 7 there is no problem. 8 has a problem that it is intersecting with the 7, and this one is 9. 9 has no problem, it is not intersecting to any edges, and similarly 10 has no intersection with another edge. So the only problem with this 8, we cannot do anything about this one. For this reason, this graph K5, it is a non-planar. Similarly, this graph, which is a K6, K33, this has 6 edges, and these are the edges, 3 edges, 3 and 3, 9 edges. So all these edges are intersecting to each other. For this reason, this graph is not a planar graph. So now we will show from the Kotkowski theorem that up the K5 and K33 are non-planar. So its statement is that every non-planar graph has a subset homeomorphic to the graph K5 and K33. So all the non-planar graph can be reduced to K5 and K33, and K5 and K33 actually are the uh, uh, actually they are non-planar graphs. So we can say that K5 is a non-planar. So this is the Patterson graph, which have a degree 3. So this is 3, this is 3, this is all have degree 7, 1, 2, 3, 6, 1, 2, 3, 8, 1, 2, 3, 9, 1, 2, 3 degree, and 10, 1, 2, 3 degree. So all have 3 degrees. So this is a Patterson graph. It is a non-planar, and we will do homeomorphic. Homeomorphic operation, that means is a deleting or adding something to do with vertices. So this is a slightly difficult, but I will make it simple. So this is a graph, which is a Patterson graph. Uh, this is a vertex 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. These are the vertices, and there are edges. Homeomorphism, vertex number 2, we will vertex number 8, we will delete this one. This will delete this one. If you delete this one, this vertex, so this will be the situation afterward. So this is the new situation. So 1, 2, 3, 4, 5, 4, 5, and 6 is there. This edge is gone, this edge is gone, so 2 edges are gone. So number 8 is gone, and this one, number 9, is gone. So we have only this edge is going 10 to 7 vertex, and then 9 to 6 vertex, and this edge is also gone. So we have this one, this graph. Now we can use 2 operations such as this one. If these are 3 vertex and 2 edges, we can smooth it to 2 vertex, 1 edge. So this is very important to know. So this is three edges. We can smooth this into two edges, two vertices. So two edges into one edge. So this is a three edges, one, two, three. We can smooth this into two edge, one, two, three edges. We can smooth this into two edges. So one, two, three. So, or this is a two edges. We can smooth this into one edge. So like this one. If you do this one, so this is 9 and 6 and 9, 6 and 5. So this can be smooth as 5 to 9, and this will be 6 is gone. So this 6 will be gone. Similarly, this one 4, 10, and 7, 10 is gone. So this 10 is gone. So 10 is gone, 6 is gone. So this 10 is gone. So from here 6 is gone and 10 is gone. So if this is gone, so 9 and 5, so 9 to 5, this one is a new edge. If 10 is gone, 10 is gone, so 4 to 7. So 4 to 7, this is a new edge. So we have a graph, this one. This is very important to know. From this one, we can shift this one to K6 or K33 graph. So this one, the same graph I have represented as a colored this one. This is the graph we have shifted. This one here, this is 3 is it is red, 7 is red, 5 is red. So now we can see this one. This is a 3 is linked to 4 and 1. So we write down a red one on top, 3, 3, 5, and 7. You can write down 3, 7, and 5. So 3, 5, and 7. 3, 5, and 7. And the rest one is a 4, 9, and 1. 4, 9, and 1. So 3 is linked to 4. 3 is linked to 4. This one. So this one. 3 is linked to 1. 3 is linked to 1. And 3 is linked to 9. So 3 is linked to 9. So these three got. Number 5. 5 is linked to 1. 5 is linked to 1. 5 is linked to 4. 5 is linked to 4. This one, this one. 5 is linked to 5 is linked to 1. 5 is linked to 9. 5 is linked to 9. So 3. 7. 7 is linked to 4. 7 is linked to 4. 7 is linked to 9. This one and 7 linked to all as connected. So these are connected graph. But there's no connection between 3 to 5 and 5 to 7. It is a connected graph, but there is no connection between these two. This one. None of the red is connected to red, or none of the white is connected to the white, vertices. So this is exactly the same as we have discussed earlier. This is a K6 or K33 graph, this one. This is a non-planar. So that means we have converted a Patterson graph of degree 10 to K5, K5 to K33. So K33 is a non-planar graph. So Patterson to K33. So this graph, whatever, that it is reduced by operation of homeomorphism. So that it comes to K33, which is a non-planar graph. So only important thing is you should be careful of the operation of this one by taking off one of this vertex, and then there will be a smoothing process of three vertices into two vertices of two times. You can do this one, and then we could convert this Patterson graph into a K33. So this is says that any non-planar graph can be converted into K33 or K5. This is the Krotowski theorem.